And what it means, what simulated emission means is that let's say again you have these two energy levels, E2 and E1, and now your what you have is again electrons present in the state E2. And now what you're doing is now you're subjecting this to an intense flux of photons, and all these photons have this particular frequency, or they have energy, which is energy of this photon is essentially equivalent to energy between these two states. So this energy of this photon, which is given by this h mu, should be equal to E2 minus E1. So what Einstein said, and this is the real genius of this fascinating dude, and what he said was, now if I have this thing happening, what these incoming photons will do is that they will simulate, or they will, another word which is used is that they will induce these electrons in the higher energy level to come down. And so this process, this flux of incoming photons, which has an energy which is equal to the energy separation between these two levels, what it will do is it will simulate, or it will induce these electrons to essentially come down and emit another photon. So now this will emit another photon. So let's say this was photon 1, so now I have 2 photons. And he said both of these photons now will essentially have the same energy. So they will both have the same energy, which is equivalent to the energy difference between these two energy levels, and they will be in exact phase, or they'll be they'll be in the same phase, or they'll be coherent to each other. And he gave multiple arguments to try to explain this. So one of the arguments he gave was each of these photons has a certain momentum. So all of these photons have a certain momentum, and when they strike an electron, they kind of push this there's a tiny amount of momentum in this photon, but it will still cause this atom to essentially get displaced by just momentum conservation. And then when this atom or this thing comes back, or it recoils, it will, to conserve the momentum, it has to essentially give out a photon which is in the same direction, or in the same phase as the incoming photon. So that was one of he tried to equate this to particles and springs and things in a spring and how they recoil and so on, because Einstein was a genius in giving these kind of arguments. And he said now the rate of this thing happening, so this thing, the spontaneous emission was derived by this formula, the absorption was derived by, rate was derived by this formula. But he said for the simulated emission, it should be proportional to the number of electrons I have in energy level 2. So it should be proportional to N2. And it should also be proportional to the density or the flux of these incoming photons. So it should be proportional to this density of incoming photons. And again, it's related by this proportionality constant B21, where 2, the subscript 21, essentially it says that it's a transition from level 2 to level 1. And then he said, this absorption process should be matched by the net emission process. So this absorption process should be equivalent to, this rate of absorption should be the equivalent to the total rate of emission, which involves both spontaneous emission, which happens on its own, and simulated emission, which is induced by this presence, or which is simulated by the presence of these photons. And so he said the net rate of absorption should be equivalent to the net rate of emission, assuming that you are in steady state, or you have thermodynamic or energy conservation. The rate of absorption should be equivalent to the total net rate of emission. And now we can further take this equation, and we can say, when would simulated emission dominate? So for simulated emission to be dominating, if the net rate of simulated emission divided by the rate of absorption should be greater than absorption should be greater than 1, and we can take these formulas. So the rate of simulated emission is essentially given by this equation. So it's B21 into N2, and it's multiplied by the density of or the flux of incoming photon, and the net rate of absorption is again looking similar, but the only thing is that instead of N2 it has this term N1. So now, and the coefficient, instead of being B21 it's B12, because it involves a transition from a lower energy level to a higher energy level. So he said this is now B12 N1, and again density of the incoming photon. So this flux of the photons, it cancels out from the denominator and the numerator. And he further said that this B21 is equivalent to B12, and so these two terms also cancel out. And now the net rate, or this comparison between emission and absorption, and for emission to simulated emission to dominate, the governing equation that I'm getting is N2 by N1 should be greater than 1, or N2 should be greater than N1. And what it's saying is that, essentially what it's saying is that if I look from this picture, I should have more number of electrons in my higher energy state as compared to my lower energy state. And this argument is what is called as population inversion. Because if you think about it, the way N1, N2 and N1 are related, that these two states have an energy difference of E2 minus E1. So if we think in terms of Boltzmann statistics, usually what we'll expect is N2 by N1 should be given by this exponentially decreasing rate. So it should be essentially given by E2 minus E1 by KT. So usually, what you would expect is that N2, or the number of electrons in higher energy level, should be much smaller than the number of electrons in your lower energy level. But for what Einstein suggested, that for this simulated emission to dominate, the reverse should be true, and this is called as population inversion. And we'll see in the next video how are some of the different ways you can achieve population inversion in semiconductors. Another way to look at it is that if you look at from this equation, for N2 to be greater than N1, one way it could happen is that your temperature is negative. So this term is positive, but if my temperature is negative, then this term, of course there's nothing called, no such thing as negative temperature, but looking at this equation, if this needs to be hold true, what needs to happen is you need to have negative temperature. And we'll talk about these things in the next video.